This is the fourth KCS talk this semester, and the speaker, of course, we know, most of you know Dr. Brent Harrison. He will be the speaker for today, and the title of his talk is
it's now lovingly AI art. How does it work?
AI art, how does it work? But that's not the title you gave me.
No.
Fine. Okay. Dr. Harrison will examine one technique in AI art generators today. That technique is the so-called stable diffusion. Okay. He will go over the details of how this system works. I'm especially interested in this statement. He says that the AI uses some special techniques to go from textual prompts to detailed art work. Okay. So let's welcome Dr. Brent
No. My heart.
Brent Harrison. The other one was a different episode.
It's okay. He is the boss, Brent. All right. Well, hi everyone. My name's Brent Harrison. A lot of people in the audience. That's nice. So I'm an assistant professor here, and today I want to talk about a topic that I've just found fascinating for the last really 2 to 3 years, forward and beyond, even though it's just recently exploded. And that is AI art, really AI creation in general, because a lot of my work is interested in how can we get computer systems, machine learning systems to be more creative, because it's my belief that that is something that's going to be needed when all of these systems move out into the world. So this is my talk, AI art, how does it work? Or, do androids dream of electric starry nights? And it is, of course, by me and Midjourney, in a little bit of irony. I did not use Stable Diffusion to make these slides. I used Midjourney because that's what I had. All right. So as I mentioned, AI creation over the last couple of years, in creation I'm using as broadly speaking to mean generating images, image synthesis, generating text, generating music. This area has exploded, mainly due to kind of quantum leaps in technologies. So we've got our Stable Diffusion, DALL-E, Midjourney, these art creation techniques. In addition, things like ChatGPT, which I'm sure plenty of people, one way or another here, are familiar with. And this is something that, like I said, I've been interested in a pretty long time, because I'm of the belief that this is something that's necessary for a machine learning system to kind of make that next step into becoming, truly social, like social beings. Now, this is something that's been around for a while, and in this talk I'm going to be focusing on image synthesis techniques, but I do think it's interesting to talk about some of the past approaches to this. And really, there's one class of technique that always gets compared to Stable Diffusion and all of the modern techniques. It's like, oh, Stable Diffusion was a big improvement. It beat the state of the art at the time, which was founded in adversarial methods. Now, adversarial methods typically involve having two systems at play against each other. And somehow, in them competing against each other, they make each other better. And that leads to an ultimately good output. If you're familiar with, we'll say, AlphaZero, self-play. This is an example of adversarial training. It plays against itself, and in learning to beat itself, it gets better and better and better and better and better. Now, the classic adversarial method for image synthesis is the GAN, the generative adversarial network. And these have been around for a little bit. I've had a couple of students, like master's students, who have looked into using these for various purposes, and they're kind of interesting. I still recommend them to people from time to time. And how they work, is this thing. So how they work is there are two networks that are at play here, a generator and a discriminator, and they are in competition. The generator is trying to generate a fake. The discriminator is trying to figure out whether or not something it sees has been generated, well, is fake or is real, as trained by this initial set here. Now, over time, the generator will learn to trick the discriminator better. Every so often, you retrain the discriminator on these new fakes that have come out, and it learns to get better. And so over time, these will both improve each other until you're getting some high quality output. People have taken GANs to a very impressive level. Some of the outputs I've seen on image synthesis using these methods are pretty cool. However, they are famously finicky. Training them is very difficult. I ran into this myself when I had a master's student who was trying to use these to create floor plans for apartments. You have to train them just right, and if you don't, then the whole thing falls apart. And it kind of makes sense, because if the discriminator is too strong, then the generator gets nothing but negative feedback. It's being told you're not doing the right thing, and so it doesn't have anything to really go on. If the generator is too good, then it can't improve itself, because it's just going to trick the discriminator over and over. So you really have to keep these close for the competition to be meaningful. And so using these is hard. It is not something that you can just pick up off the shelf and go with. Tuning them is tricky. And that was really one of the big motivating factors in why these newer approaches came about. And so here's an example of the big three currently in image synthesis. So Stable Diffusion, DALL-E 2, is there DALL-E 3? It's still 2, and Midjourney. Now, Stable Diffusion and DALL-E 2 are both, we know that these are based on some kind of diffusion network. Midjourney is proprietary, and so it's kept under lock and key, so we're not quite sure. But it's believed that this is something that's going to be based on a diffusion network. And that's really what I'm going to be talking about today, is the basis that makes all of these things work. Although it is kind of funny, you can download pre-trained models for both Stable Diffusion and, well, probably DALL-E 2 that allow you to recreate Midjourney images. So we're entering into a really weird world of legal problems, and that's a talk for later. That's just as interesting, I think. Okay, so I'm going to be talking about diffusion models. So what are these things? How do you get them to create from seemingly nothing a brand new image? Now, how they work is, well, okay, here we go. So what I'm going to be presenting here is from this paper. This is considered kind of the first paper on diffusion models for image synthesis by Jonathan O et al. Out at UC Berkeley. So everything I'm presenting here is pretty much what's in this paper. Now, I will asterisk all of this. This is an incredibly dense paper. This is an incredibly dense topic. And I'm going to present things to you like, here's the math that makes a lot of this work. I'm going to try to do it in a way that's approachable, because there is a lot of complex things that allow you to do this training. So if you find that interesting, look into the paper. I'm going to try to keep this as high level as I can, and hopefully won't get lost in the weeds too much. So wish me luck there. Okay, so at its core, what is a diffusion network learning to do? It's not actually, well, you can think of it as not really learning to create an image from scratch. Instead, what it's doing is it's starting with Gaussian noise. Gaussian noise. And over time, it's learning to remove that noise, piece by piece by piece. And if you do that enough times, you essentially remove all of the noise from the image, and you're left with, in this case, flowers at the end. And so in a GAN, or in really any of these adversarial approaches, you're typically learning to make the image, well, the original task is, I'm going to make this image. Here, my task is, I'm just going to remove noise, and what's left will be the image. And so the big question is, how exactly do we get to this point? And for that, we have typically two processes that we're going to look at. One is a forward diffusion model that's going to describe how does noise get injected into a denoised image, and there's a reverse diffusion model. That's where all the magic happens, which is, okay, well now that I can go forward, how do I go backwards from there? How can I take pure Gaussian noise and remove noise from it until I have a nice pretty image at the end? So forward diffusion. At its core, and this is a common thing throughout this approach, at a high level, conceptually, it's very, very straightforward. And so forward diffusion, no different. So the idea here is we're simply trying to learn this cue. This is a conditional probability model, and it is the probability, or this is essentially the process of adding noise to your base image. X0 here is my nice, pretty denoised image that I've sampled from my training set, and the forward diffusion process says, over time, just add a small amount of noise to it over and over and over again. And so you can see, as we go along some number of time steps, we're adding more and more noise. Past a certain point, this certain point doesn't really matter. The idea is that once you've done a sufficient number of time steps, I think in the paper they did 500. The assumption is that all you have left is just noise. That's it. And so what we're trying to model here in forward diffusion is this. Conditional probability of xt given xt minus 1. That also means, note, that this is Markovian. That simplifies things a bit, as we'll see here. So how do we add this noise? What does this look like? It's not just, there is a little bit involved here. So given that the noise itself is defined by a normal distribution, we can simplify this. All we care about then are the mean and the standard deviation, or in this case, covariance matrix. So if we know those, we know the normal distribution. And thus, we know, hey, the conditional probability distribution, which is great. Using that, we can recreate the forward diffusion process just by multiplying these things together. So repeatedly applying the noise at every time step. Cool. This is sometimes referred to as the trajectory of the noise application. So this is cool, right? I did it. I finished it. This ended up being really easy. Or is this problematic at all? Is there a reason why we might not want to do this? Yeah. Oh, yeah. Hand up. Cool.
Guessing if you had too much noise, it might be too difficult to remove some out of certain areas.
Oh, so you think that, but that's actually kind of a benefit. You can't have too much noise here. What's nice is that, again, once you go far enough, we assume that all you have there is just noise sampled from a Gaussian. The problem with this is that I don't want to have to reapply it 500 times. If I want to see an image that is, here's the resulting image after applying noise 500 times, I don't want to have to go through steps 1, 2, 3, 4, 5, all the way up to 500. Because notice, this product is from 1 to t. And so during training, I'm going to be needing to generate these images, or generate images at various t's. And so if I have to constantly calculate this all the way out, that's inefficient, and we're lazy. So that's the problem. And so that's the first problem that the authors needed to tackle, was how exactly can we do this efficiently? And that they solve using a reparameterization trick. This is actually something that's really common in variational autoencoders. Another generative method that can be used, or that's been used in the past. And so here, weird math part 1. So what they do is they reparameterize the mean and the standard deviation in terms of this parameter beta. Now beta is a hyperparameter associated with the process. It's essentially the variance with which that you're adding noise to your image. And it typically runs on a schedule. The important part about this is you know it beforehand. So you don't have to learn it. It's defined by you. And so by redefining our mean and standard deviation in terms of alpha, which is defined based on beta, what we can do is rewrite the mean and standard deviation in terms of only a single image, x0, our starting image. Now this might not seem like much, but what this means is that at any point, I can sample an image that has an arbitrary amount of noise in it that's associated with a specific time, t, without having to go through all of the intermediary steps. So this means during training, I can arbitrarily sample noisy images that follow the schedule defined by beta, which is huge. Now some of you might be scared of this product here. I don't actually know if any of you are scared of that product here, but the product in the last slide was bad, so like why is this one not bad? Because we know beta. We pre-computed it. So what we can do is actually, for our entire schedule, pre-compute all of our alpha values, which is exactly what the authors did. So that gets taken away. So at the end of this process, the whole big thing that we were trying to do here is just get to this point, where now we can arbitrarily sample noisy images at any time using only our starting image. Beautiful. So this ends up being useful because when we go to kind of try to figure out our target that's used in our loss function, we're going to end up needing this. So I mentioned that beta operated on a schedule. And so this, I just wanted to give some more information on what exactly that does practically. So beta ends up determining how much noise gets added, how fast. So in the original paper, so this is an example of two schedules and how it's going to change the image. On the top here, we have a linear schedule, and this is the schedule that the authors used in the paper. And so as you can see here, we start with our denoised image, and as you go, more and more noise gets added at a relatively constant rate. It's been shown afterwards, after the fact, that different schedules can be beneficial. This one down here is a cosine schedule. And so you notice that towards the beginning, noise is a little slower and it picks up at the end. There are a bunch of these schedules. Yeah, this is just mainly to give you an idea of what does it look like in practice. Okay, so now where the magic happens. Reverse diffusion. So forward diffusion, again, we really wanted to get to this fun sampling outcome, but reverse diffusion is where we learn the big part of stable diffusion. This is figuring out how we can go backwards. If we start from some arbitrarily noisy image, or, if you're feeling spicy, just noise that you sample from a normal distribution, how can we turn that into some, I call this an original image, but really it's just some image that has no noise in it, because you don't necessarily need any reference here whenever you're making these. So much like the forward pass, we're learning a conditional probability distribution. In this case, it is x at t minus 1 given x at time t. Makes sense. And the same rules apply as the forward diffusion. This conditional probability distribution is Gaussian, so we can describe it using mean and a covariance matrix, sure. And importantly, if we knew what this was, if we knew, in this case p, and I'll talk about like why there's a little delta here, or theta here, if we knew this, we could go backwards. We could just repeatedly apply this to our noisy image and end up at p0. This here represents the trajectory that will take us back to 0. So if we know this, hooray, we've done the thing. Now again, some people might be questioning, well, why can't we, this is a conditional probability distribution. I took CS463. I know Bayes' rule. I can directly calculate this, right? No, you can't. Or I should say, you could, but it's going to require information about your underlying image distribution. So the distribution of x0s, which we don't have. Or it's intractable, really. So we're left with this, trying to estimate this, this probability. And this is parameterized. So originally, in the original formulation, the idea was, okay, we'll use some kind of neural net to do this. this. And since it's a normal distribution, that breaks down into just using the neural net to predict the mean, mu, and the covariance matrix. So now these are your parameterized things. But as we go on, more and more, we're going to get this neural net to predict less and less. Oh, and also, feel free to just stop me at any time. Although again, a lot of this is super deep math that I don't fully understand. I put the stuff I did understand in here. Okay, oh yeah.
Sorry, could you explain again, Professor, why the neural net may have not been working as expected?
No. The neural net works as expected. It's just if you wanted to directly, so again, this is a conditional probability distribution. These are things that, in some cases, you can directly calculate. However, in this case, you can't. And you can't because if you were to decompose this using like Bayes' rule and whatnot, it's going to require you knowing the probability of an arbitrary x0. So you need to know the probability distribution of your underlying set of images, which is intractable to calculate.
Could you iteratively keep guessing for programs to iteratively keep guessing for close enough?
I mean, at that point, it's going to take so long, and it's like such a small chance of just guessing it that it would never finish. So that's, again, when I say it's intractable, that's what that means. That's what we're getting at. Like, if given an infinite amount of time, maybe you could, but under our constraints, out of luck. Which is why, and in those situations, that's like the perfect situation to use machine learning. So instead of trying to directly calculate, we estimate. Okay, so our goal during this training step is we want to use our neural net to predict mean and standard deviation of some normal distribution. However, the authors, what they did was a little bit of a cheat, which is fine. I love cheats. They instead said, okay, we only care about predicting the mean. We're going to hold the standard deviation constant, or the covariance matrix constant. Focus on the mean. So the rest of this is going to go forward assuming that all we're trying to do is predict the mean of this normal distribution. Later on, someone came along and said, oh, well, here's how you would predict the standard deviation at the same time. And of course, they showed that, yes, this is better, but we're presenting the first paper. Okay. Ugh. So the goal is to predict U hat. This is the target that we want to, that we're trying to predict. So the first thing that the authors did is they used their insights from the forward diffusion process to rewrite mu. Again, in terms of these alpha values. And that gives us a way to somewhat directly calculate this target value. And again, I should remind people that you need this target value because when you're training, you have to know what you're trying to predict. You use this to get to loss. Anyone see a problem with this formula, with this big math ball here? Because there is a problem. Something that makes this such that if we were testing, like, okay, imagine we were testing. And we have to and we're using, like, again, a lot of this stuff we know to begin with. And we want to calculate mu. Could we do it using this formula? The answer is easy, because I wouldn't be asking if you could. So, like, the answer is clearly there is a problem. Like, no, you can't use this. But the more interesting thing is why. Any ideas?
You don't know x0.
Boom! Yes! You don't know x0. I'm sorry if I peeked the mic. Yeah, so when you're testing, what is x0? x0 is the original unnoised image. Except when you're testing, all you have is xt. You have noise. And so where does this come from? The answer is nowhere.
You just make it up.
No, you can't make it up. I can't do this. And so, it seems like we're out of luck. Except some people that are much, much smarter than I am and much better with math said, no, we're not actually out of luck. We can continue to reformulate things. So we can rewrite x0. And this is using, again, the reparameterization trick that we talked about earlier. And what this does is it rewrites it solely in terms of xt, which during testing, we do know. Because, again, we can arbitrarily sample this at any time. But in doing this, we have this extra little parameter here. Its name is epsilon. This is just, you can think of it as the noise itself that we've sampled from some normal distribution. So if xt is the noised image, epsilon are the actual values that you're adding to those pixels to add noise in there. And so now this is the big thing that we don't quite know. And it turns out if we did know that, we could calculate this whole thing. Oh, oops, sorry. Because beta, we know. Alpha, we know it's in terms of beta. Hey, that, yeah, we know that. Xt, we can sample that. Epsilon is a question. But now we don't need a neural net to predict mu. We need a neural net to predict epsilon. Again, it's moving goalposts. Moving goalposts. But that's how this works. So now, in order to calculate the mean, what the authors do is they train a neural net to predict mu, or not mu, epsilon. And once they do that, they can simply, and this epsilon is just drawn from a normal distribution. And because of that, you can sample this during training, and then essentially just calculate the squared error between what you sampled and what your this is just a fancy way of saying what your neural net says. And that's the loss. It's a standard loss that we use in 460. Yeah?
Sorry, what is epsilon then?
So epsilon, you can think of it as, so imagine an image. 2D, 3D volume. In the image itself, you've got pixel value, 0 to 255. Epsilon is a matrix or a volume of the same dimensions, but instead they each have numbers sampled from a normal distribution. This is your noise. And so if you wanted to add the noise to the original image, you could just moosh them together. And now you have a noisy image. So that's what that epsilon is, and that's what we're trying to predict here. Because if we knew that, we could calculate this mean, and then we could, as we showed previously, iteratively remove noise until we get back to an original image. So all we need to do is predict this, and this is the loss function that will allow us to do that. Yeah?
So x0, xt.
Yep.
Is that basically, what would that look like? Is it just like a 2D, is it like a 2D array of RBG values?
3D.
3D array.
Yeah, it's got to be a volume. So like going back, where is it? No, I don't want to use that. Where are my cats? There, or oh, it's a dog. Okay, there they are. So yeah, each of these is like a height by width by depth volume. X0, and really x0, xt, they're all the same. They're all kind of the same. It's just that x0 has no noise added to it. So they're all the original pixel values. As you move on, so like xt, that now has some noise added in it. And all that noise looks like is a number that's been added to your original pixel value. So all of these little fragments that you see here, that's because the original pixel value now has some number drawn from a normal distribution added to it. And so the color shifts. And so that's what's going on there. Yeah?
Is that later giving you a way to find initial noise?
The beauty of this is you don't need anything special to find your initial noise. The way that it's set up, you could sample any noise from a Gaussian distribution, and you can still use this just as it is. And in fact, I think that's where I was. So all of that, maybe nastiness, I don't know, just leads us to very simple training, very simple testing, or sampling. So for training, all you do is sample an initial image, x0, great, we have that. Sample a t uniformly from your schedule. So it assumes that you're going to have, at most t steps. T was 500 for the authors. And then sample some noise from your Gaussian. And then update your weights according to this loss. It's really that simple. Because all you're trying to do is predict E. Yay. Or epsilon. For sampling, So XT, you just sample some starting noise. And luckily, any noise will do, as long as it's from this distribution. And then slowly but surely, you move backwards. You go from big T down to 1, and you're going to, and this is the process of removing noise from your image. And so remember, alpha is based on this variance schedule, so it is trying to remove noise according to that schedule. And so you end up with my noisy image minus the noise that my neural net predicts, essentially. And that's why, like, how many people have used a system like this before? Okay, you have. Nobody else? Okay, we're gonna have some fun. Okay, so I have Midjourney here. This is what I use to create all of my slides. It's just a Discord bot. How this works, so I say imagine. I can put in a prompt. Give me something. Yeah.
Dogs fighting cats.
Dogs fighting cats, beautiful. Dogs fighting cats. Let's see what it does. I've been doing this for everything because I want the aspect ratio to be big. And so we'll see how long this takes. But how it generates is you can actually kind of see the denoising process as it goes. And so what it'll start with is, and it shows here once it starts in percentages, here it is. So you get an initial noise. And as it goes, you might, like, it's going to come more and more into focus because what's happening is more and more of that noise is getting removed. Yeah.
So it started with complete Gaussian noise, right? Like it doesn't show you the first step.
No.
It once it's in movement, it's Gaussian.
Yeah. And also what's going on, and we'll talk about this a little bit later, is this is being conditioned on the prompt that I gave. And so that initial noise does have a small amount of conditioning coming from the fact that I said dogs fighting cats. But yeah, like after that initial thing, it's just constantly removing noise from it until you end up here. Oh, I like the lightning cat. That's pretty good. And so like, I thought this was, when I read how stable diffusion worked, I thought this was super cool because you can see it essentially like do the sampling in real time and see the effect that all of this has. What we'll do later, if there's time, because again, I'm pretty sure there will still be some time. We can play with that some more.
Why are there 4 pictures?
There are 4 pictures just because it, for usability purposes, it's always going to generate 4 at a time. So it's actually running that sampling process 4 times. So it's not the nature of the algorithm, it's just Midjourney wants you to have a bunch of things to pick from, so it gives you 4. I think you can actually change it so that it will do like 6 or 8. Dolly and like the online Dolly portals, they would do 6, I think, as their default. Yeah, but that's what's going on there. Yeah.
So you frequently hear how scalability works well with these kinds of models.
Mhm.
Like, you increase the number of trainable parameters in one instance to another. How does that fit into this?
So remember, epsilon is what you're trying to predict. And so when you increase your number of trainable parameters, it's all happening there. So this theta here, that represents your parameters. And so whenever you're scaling, you're just saying, oh, add more parameters to this. And so that's, yeah, where the power comes from. And it's the same for any other parameterized model. Yeah.
So, oddly enough, I kind of get to this.
Oh,
But,
I did it.
yeah, but the thing that has bothered me about this is, okay, so how does the prompt actually play into this?
Okay, so I wish I would have put those slides in here, but I can tell you. I'm going to skip forward a little bit. I'll come back and go through all of this, but we'll go to here. This is kind of the big finish and reveal of the whole talk, because this is how stable diffusion works. So I'll direct your attention over here, conditioning. So what happens here? So this is the role that the text prompt actually plays in things. So what it's doing is, are you familiar with CLIP? No? Okay, so CLIP is an OpenAI technology that is meant to calculate, or it connects images and text. And it does this by calculating embeddings. So image embeddings and text embeddings. And it allows you to calculate their similarity in a latent space by calculating the dot product between the two. So what happens is, when you're generating things, you take, you need an image and you need text. Where the text comes from is pretty obvious, your prompt. Where do you think the image comes from? Noise, yeah. The image is that noise that you generated. So what's going to happen is you're going to calculate the clip embedding for your noisy image. You're going to calculate the clip embedding for your prompt, and you're going to multiply them together to get kind of a similarity value. That similarity value gets passed into this is the backward diffusion learning step. And so this is is guiding the denoising process towards specific things. So that's why you notice those initial, like the initial noised images, kind of had figures already. So some of that is because, again, there's some amount of denoising happening before that, but also because the prompt itself is doing some initial guidance towards different things. So that's where that comes in. Okay, back. Here we go. Any other questions? Okay. This is the process. So I've said nothing about what this neural net looks like. It is notable kind of what the architecture of this epsilon neural net is. So it is a U-network. This is another thing that's kind of cool about this. It's all using technology that's just kind of out there. So each of these like segments is a ResNet block. So another kind of common image processing neural net. And so a U-net is simply a series of like dimensionality reduction operations. You get to the center here where we have this nice little context or embedding vector. And then over time it's going to try to upscale the dimensionality back into its original dimensions. What's notable, and so it makes this fun U-shape. What's notable about a U-net is you have these skip connectors at every level. And so if you can see, which I don't know if the numbers are big enough, if you look at the dimensions here, so this is a 64 depth vector at this level, all that happens with these skip connections is they get concatenated to the front of what comes up here. So this is now 128 at the first level because it's 64 plus 64, and then that gets kind of, fed forward. Here, 128 gets concatenated to another 128 to make 256. So this allows you to get some information from previous, from earlier in the network to go forward to the next part. These kinds of skip connections have proved to be pretty beneficial in other areas as well. But this is what that epsilon network looks like. And remember when I said, like, you asked, what does noise look like? So again, this is going to get you an image in the same, an output in the same dimensions as your image, but it's just going to be full of noise values, noise that you'll ultimately add back into the original image to create an XT, or remove from a noised image to sample. Okay, last problem. So I spent a lot of time talking about, so those are diffusion networks. Those are vanilla diffusion networks. Any reason why they might not be super great? So scalability has been mentioned. I would argue that diffusion networks by themselves might not scale the best in the world. There's a reason for that. The reason is because all of this has been done in pixel space. And images can get pretty big. And so if you're doing this in pixel space, yes, maybe you'll scale decently, but it's still pretty inefficient. Enter, and this is how stable diffusion works, latent diffusion. So they took ideas from, more ideas really, from variational autoencoders and said, well, what if, instead of doing this all in pixel space, we took the image, we ran it through an encoder, and now it's magically in a latent space. Could we still run the same diffusion process? And it turns out the answer is yes. So now, instead of adding noise to an image, you add noise to a fixed length vector that represents that image. So instead of dealing in this height by width by depth original pixel space, you're dealing in a fixed latent vector space. And that's where we get to here. And so the whole thing is, we have X, our original image. Here, epsilon is an encoder. And that encodes your input into this Z space. And so Z space is just, think of it like a 500 length vector of numbers, and that represents the image. These go through the diffusion process so that we can generate a ZT. It's the exact same as the diffusion process in pixel space. It's just you're adding noise to vectors. This then gets sent through the backwards process. It learns, again, this is the same. I'm learning how to noise, or the noise in my vector. This gets repeated until I get my original unnoised Z back. And then in order to get an image, in this case a little X squiggle, I have to run it through a decoder first. And so it's the same process as normal diffusion, but in a latent space. Now it's more efficient. Yeah.
Some of the conditioning stuff are using the latent space version of the image.
Oh yeah. Which actually makes more sense because the embeddings themselves are in a latent space, and so it kind of fits. But it is kind of interesting to think about. Noise in the latent space translates into noise in the pixel space, and yet it's still done in a way that makes sense. The same kind of thing happens in variational autoencoders, and I'm still fascinated by those. So, like, yeah. So that's the thing. That's it. That's how stable diffusion works. So my conclusion, so these systems are, in my view, like, fascinating. They, I made sure to look this up beforehand, because never has a quote that I've heard, I don't know, used in the world, I think applied more than Arthur C. Clarke saying, what is it, any sufficiently advanced technology is indistinguishable from magic. This stuff is magic to me. How it goes from nothing to something, and something that is way better than I'll ever be able to create. And these systems aren't going anywhere. I don't think so. Which actually leads into the next talk that I'm going to give, which is the very many legal issues that come along with this technology, because there are plenty. And in my view, a lot of this year, and probably the next few years, are going to be us dealing with this and trying to figure out how do we, not how we put the genie back in the bottle, because we can't do that, but how do we live with the genie now that it's here? Same thing with ChatGPT. So anyway, that was my talk. Questions? Yeah.
So, in the work that involves, like, training on stuff, like, at what point does somebody ever need to, like, look at a bunch of images, or someone or something, maybe look at a bunch of images and put labels of, like say the cat and dog fight. Did somebody need to get a bunch of images and put tags on them that's a cat, as a dog, cat and dog, cat dog fighting?
Yep. Clip does that. So Clip, again, is trained on these giant image captioning repositories. So it would be like, oh yeah, here's an image of a cat and a dog. Maybe not necessarily fighting, but like, oh, here's a cat and a dog. And so it would have a caption, you know, cat and dog. When you cast those into a latent space, you get kind of interesting semantic information about both of these things. You get image features, you get semantic features from the text, and those get combined. What it might have done is, in the fighting case, saw another image of, oh, here are two animals fighting. Ideally, if the latent space is made correctly, which in this case it is made correctly, it can then combine those two ideas by simply maneuvering around the latent space. And so the idea of a cat and dog fighting might be somewhere in between the locations of an image of a cat and a dog and an image of two animals fighting. And so yeah, there is, so the initial training comes in with like Clip there. Yeah, and those systems are out there. Like you can play, I think Clip has an online way that you can kind of mess with it. We've looked at it for some of our other projects with like comic strips and whatnot. Any other questions?
Show us another demo.
Yeah, I was gonna say I can go back to playing if you want. Okay, give me a prompt.
Gaussian noise.
Gaussian noise. All right. I don't know what this is gonna do. This will be fun. Imagine Gaussian noise. Let's get a good aspect ratio. 16 by 9 Gaussian noise. It'd be great if it just went, oh yeah, I know what to do. Bam, it's out. No denoising needed. So one of the, oh yeah, well, any other questions while it's trying to noise itself? Yeah.
training, it's forced to denoise. Can it actually generate noise, like film grain or something?
Apparently not. So yeah, my guess would be probably not, because it's trying to remove Gaussian noise, asking it to create it. Probably tricky, because it's just been trained to constantly remove that. Now, I do wonder if you could make it, probably not here. And also remember, clip is trying to connect these things together. So a lot of it depends on, can clip identify noise? But I wonder if you could get this to give you like non-Gaussian noise. Okay, so we got like some fractal type things, I guess. That's interesting.
It can generate like film grain. Like if you
Film grain?
If you tell it to generate like an 80s like vintage like
Oh.
image, it'll give you like film grain.
Yeah, but I don't know if it could give you like TV snow.
Oh.
Like, yeah, do TVs even have snow anymore? There's no signal coming in. But yeah, I don't know if it could do that. It could, yeah, it can definitely. Let's see, film grain. Let's make some stuff here.
Castle on a cliff.
Castle, castle on a cliff, overlooking a bay, film grain style. Sure, let's see.
There is actually some with having it generate images taken by specific different models of digital camera.
Oh, that's super
And
fun.
it actually came out fairly recognizable.
Yeah, I mean,
Color profile, things like that.
and like as more images get kind of, released into the world, that's just more stuff that gets fed into its training set. And so it's able to kind of, keep the process going. I think we're going to get some good stuff here.
Is this running on your laptop or on this?
This is a cloud-based thing. So Midjourney, this is a Discord bot, and so it's doing everything on the cloud. You can download Stable Diffusion. There's a GitHub repository that you can just run, and it does run. It probably won't run on my laptop, but you can run it with surprisingly low resources. I think what was Indy doing, like a 970 NVIDIA card, he was able to get it to run decently well. Oh, there it is. Yeah, you do need a graphics card. Okay, so film grain, I don't know. Well, that bottom one I kind of like, but incredibly detailed. And it's definitely a castle on a cliff overlooking a bay. Yeah.
Okay, so that end.
The end thing.
Stable Diffusion diagram.
Oh, yeah.
Yeah. So ZT.
Yep.
That's like a collection of images after a bunch of filters of Gaussian.
It's a vector.
Okay.
Simply a vector. It's not an image. It's a point in latent space. And so imagine if you have like a 500 dimension space. You can represent that as a 500 length vector. You fill that with numbers, and that is a specific point in that space. So this represents the point Z after we've injected noise into it t times. Except we haven't really injected noise into it t times. We've directly sampled this because we showed that we could do that, only needing to know the initial state.
Okay.
So this is a noisy version of the vector Z.
Yeah.
Yeah.
And so was Z at some point a numeric representation of it?
Yes, that is exactly what it is.
And after you've added a bunch of random distribution of numbers onto it, you have ZT.
Yep.
The ZT in the bottom part, is that the same ZT?
Yes, because
So
what
it's
we're
rolling from the same height.
yes. Well, and yeah, because what we're doing, and I can go back to the here. So we still need to come up with a T. Here is it's a different Z here, because this is a different thing. But XT is a thing that we create from this noise. And so then what we're doing, like during the training step, we sample it and we work backwards. So we start from that T and we're going to denoise it. We try to predict that epsilon. So back to, so yeah, these are the same.
Yeah, okay.
And then this gets passed in as input. I guess this is the sampling part of it.
So you said that, so like at the point where I'm training on prompt and stuff, you're saying it's an it's doing some like denoising already and stuff.
It's not. Well, Clip is pre-trained. It is pre-trained, and they're not doing any additional training using, or on Clip, I should say. What they're doing is, this thing represents an image. So you could actually get Clip embeddings for it, even though it's just noise. And so what it does is it gets a Clip embedding of that noise. And then it has a Clip embedding of the prompt. And it compares those together and calculates a similarity between them. Chances are it's going to be pretty bad to start off with. But that similarity gets used to condition each of the denoising steps. So that as you get closer, what you're trying to do is make the image or the noise that you're generating here match that caption. So it's kind of guiding the denoising process to make it so that your image and your caption are appropriate at the end.
Yeah, I guess my question is like, are we just picking out? So as I know, are we just picking out 4 really staticky, blurry images that through Clip have the tags that match what we're like typing in? So, yeah, like 2 amplified, you can have like these really staticky representations of images that just are within a certain, I don't know, I guess, parameter or distance away from like, oh, these things, are closely matching up to what we're talking about, even if, and then we just let math kind of denoise it until we get something close.
Think of it more like this. Think of it like I start with noise. I can look at my embedding to get some value for that, sure. And I start with a prompt. I look at how they're compared to each other to get a similarity. Originally, it's going to be bad. Ideally, I want to denoise things, and there are a bunch of different ways that I could take the noise out. But I want to do it in such a way that that similarity gets closer or gets higher. And so, if I wish this saved any of the noising steps. But as it would go along, what it's doing is it's saying, okay, well, I'm going to remove noise in such a way that now my Clip embedding for the image and the Clip embedding for the prompt is higher. And I'm just going to keep trying to drive that value higher and higher and higher. So it's not, don't think of it necessarily as it's picking images out of something. It's more, it's removing noise so that the resulting image is closer to the prompt than it was before. So I think you had your hand up and then...
So it creates noise and then it adjusts it until the similarity value with the Clip caption is high.
Yes, yeah. That's it's a bit of a simplification, but that's a good way to understand it.
Is it like back propagation training every single time? Or
So yeah, that does get incorporated into, I think it does get incorporated into the loss function, so that does get backprop a little bit. Clip doesn't get backprop. No, the Clip doesn't change.
It's already trained.
Yeah, that's already trained. But the U network does end up using it, and I wish I would have put this in here. It does end up getting used in the mean calculation as well. So yeah, those are the 2 places that it gets incorporated.
Can you use the same ZT over and over again and not calculate?
So you could.
It's just random noise.
Yeah, it's random noise. And now I'm trying to think if the denoising is deterministic. Ooh, it might. Actually, yeah, it is. The denoising, I think, is deterministic.
So which picture you end up with here depends upon which random you started with.
Yeah.
You can build random noise without a lot of work.
Yeah, that's one of the benefits is you don't need to start with anything fancy. It's just random noise. It's easy to sample from that distribution. Yeah.
Yeah, so the one thing that I've noticed they always do terribly on is basically image invariance.
Oh, yeah.
Things like, for example, how many fingers are on hand?
Yeah, oh yeah.
Or what does actual text look like?
Yeah, oh man, I've got a couple of good
Yeah,
examples.
Can you say something about how they might fix that? Or
Oh boy, I have no idea. Because yeah, this is such an uncontrolled process, and those are such fine. Yeah, okay, this one's good. one hand we got 4 fingers, on the other we've got like 8 or something. Yeah, you know, it averages out.
One too many, one too few.
So yeah, like solving that, I'm just not sure. Other than,
You have to restrict the range, right?
yeah, but you have to even like know what the range is, which is the problem, is that in that latent space, you lose all information, or at least as a person, you lose all information that comes back here. So unless, and people have gotten better, like systems have gotten better at this, and I don't know how, but like I wonder if you could map out that latent space as to how certain moves affected the image. That might be able to help you restrict things a little bit more. My favorite is, where are you? This one, because of my little tentacle guy here. Originally, this started out as a hand with 3 fingers, and then as it upscaled, it just said, okay, screw it, these are tentacles now. Yeah.
And the chessboard.
Oh yeah, and the text also. Oh yeah, and the chessboard, this is not a game that humans play. My wife said when I showed her this, she was like, oh, that's the standard starting move of build a perimeter. Build a perimeter defense. Oh yeah, he's Magnus, that's how he does it. Yes.
I know in
Oh.
there is some work in attempting to prove points
Mhm.
by instead of getting the actual network to prove them, or making them better, is recognize where the weak points are and using some other system to sort of.
Yeah, I
this
could-
is like for fact checking, I think, or something.
Mhm.
So you can, given a prompt to a transformer, you can recognize, oh, you want me to do something that requires fact checking.
Mhm.
So it will use something like Wolfram Alpha
Yeah.
to get that data instead of the transformer.
No, that makes sense. It might be easier in this case. So if you're working with this image, just say, okay, identify the parts that don't make sense, and then alter it to make it make sense. So like, yeah, figuring out that Magnus has 8 fingers or something, or that this is not chess, might be easier than trying to do it at at the latent stage, where it's kind of the Wild West.
All right, we have to stop here, okay? Before you enjoy the pizza, please sign in. And I have a personal question for you.
Oh no.
Have you thought about the idea of changing into the acting career?
When I should, right? I should just stop being a professor and just go into acting.
Thank you very much.
No, thank you.